So then welcome back to the last session of today's workshop in quantum software. Let's see what this last session will do, but it definitely starts with one keynote speech from Raphael Seidel, and he's from the Fraunhofer Institute, I think Focus, right? Yeah, that's the short name of it. And he's going to present some part of the QRISP software part, and that's Jasp, right?
Exactly.
So, stage is yours.
Yes. So, first of all, thank you very much for inviting me. It's been an honor, and I hope I can make it up to you by presenting some interesting things. Okay, so first of all, I know that there are some people in this room who are already a bit familiar with QRISP, but I would still like to repeat some of the things that we have been doing before I get to the new stuff, because I don't want to lose anyone. Let's start with some motivation. What is the motivation behind QRISP? There's this insight that the further we progress in the area of quantum computing, the more I believe focus will come into software development. And we already saw this in the regime of classical computing, where in the early 1950s it was mostly hardware that was producing cost, and as the hardware matured, we saw that software maintenance and development became the source of the larger share of the cost. So, I say this because developing a high-level quantum programming language, to some people it seems like some kind of academic endeavor that might be interesting, but not that much monetary motivation. But no, there's also a commercial motivation here. And there's also a more recent example of this phenomenon. There is NVIDIA versus AMD, and as you see in this chart here, the AMD GPUs, performance-weighted, also regarding cost, they outperform the NVIDIA ones. But NVIDIA invested and started building their software much earlier than AMD, and now their shares and their value outperform AMD by a lot. Okay, so now I want to rant a bit about programming with quantum circuits. So I believe that programming or quantum circuits as a programming model are a dead end. And why is that? Because they prevent developing software collaboratively. And there are two problems that stand out. I call them the signature problem and the modularization problem. And I'm now going to talk a bit about what that means. So if you develop a code base with other people, you kind of want to let them know what your code does, right? And for that, we have documentation. And the documentation ideally tells you, I need to plug this here and this there. And if you're programming with a quantum circuit programming model, then that's basically not possible, because what you plug in is simply said a huge list. And then you kind of have to indicate, so index 0 to n is the input 1, index n plus 1 till 2n is input 2, and so on. So that is clunky and error prone, and not suited to have large-scale code bases. In Qiskit, they also face with this problem, but they simply don't document the signature. So that's also one way to deal with it. Okay, the second problem is the modularization problem. So what does modularity here mean? So basically, what I'm trying to say is that if you want to develop a code base effectively, you kind of need to modularize certain parts of the code that they don't have that much interaction with each other. Because if you do that, then you can exchange the modules, you can benchmark, bug fix them in an isolated matter, and also optimize them, of course. So modularization is really a core feature of software development, of classical software development, and it should also be the same for quantum. But if you're using a quantum circuit programming model, then you can't modularize your code base. Why is that? The reason for that is memory management. Because let's assume you implement a model and then a module, and then you want to implement a different version of this module, but performs the same task, takes a different amount of ancilla qubits. Then you somehow need to figure out, if you want to exchange the modules, where are these ancilla qubits coming from? Where are they going to? Basically, you have to tinker with parts that are not part of the module, right? So it's not really possible to embed this into a modular fashion. There's this example here with two quantum adders. It's the Gidney adder and the Cucharro adder. And the Gidney adder here requires 2 ancilla qubits. In general, it requires O of n ancilla qubits. And the Cucharro adder only requires a constant amount of ancilla qubits. And now you want to implement your Schoß algorithm, and you want to quickly exchange the adder because you want to test the performance. And if you program in a circuit-based programming model, then this is going to be a huge mess because you have to completely rewrite your code to fix the ancillas that are that these adders require or don't require. Okay, so well, this motivates CRISP, which is a high-level quantum programming framework, and it is centered around quantum variables instead of qubits and gates, and it significantly enhances many aspects of quantum software development, like fast prototyping, code size maintainability, and other stuff. It's fully open source with a lot of documentation on this website. You can also install it with pip install CRISP. We also already did some cool things with CRISP. We implemented the quantum backtracking algorithm by Ashley Montanaro, which has been published about a decade ago, but so far there were not really that much, well, 0 implementations basically. So yeah, that's cool, and also shows how these advanced software engineering techniques help you to do these things that supposedly were not possible before. And together with some researchers from Alice and Bob, French quantum computing company, we implemented one of the first fully compilable elliptic curve logarithm implementations ever. There's also state-of-the-art performance. So this plot is a performance benchmark of Schoß algorithm, and we see here that many of the relevant fault-tolerant metrics, so t-depth and t-count, they're much better than the competition. Regarding the NISQ metrics, they're also better, but the advantage is not as elaborate, but yeah, still. Okay, so there's also a module for performing Hamiltonian simulation, in particular quantum chemistry. Here we benchmarked against the Google package OpenFermion, and yeah, we noticed that we could reduce the amount of arbitrary angle gates by a factor of 20. Why arbitrary angle gates? In a fault-tolerant machine, these kinds of gates need to be synthesized by some kind of approximation procedure, and these are really the thing that makes a Hamiltonian simulation costly, so it is natural to benchmark them. Okay, so short framework overview to understand a bit how programming with CRISP works. We're gonna solve a really simple problem, this equation, and we're gonna use Grover's algorithm. We're not gonna achieve quantum advantage with that, but it might show you a bit how it works. Okay, so first of all, we're gonna implement the oracle, and the first thing that you might notice is that contrary to other programming frameworks, Oracle is not really some kind of circuit object. No, it's just a Python function. And within this Python function, we see some infix arithmetic here operating on this quantum float. We see a comparison, and then we see the phase tag, which is also required for Grover's algorithm. And this is the underlying circuit. Yeah, I should probably mention, so CRISP is like 100% compilable, so everything that you write can also be run on actual backends. So there's the circuit. So yeah, basically we see the steps that we saw before. We see the multiplication evaluation. We see the comparison with this multi-controlled X gate. We see the Z gate, and something that I didn't really highlight that much, it's the auto uncompute decorator. This decorator basically analyzes the function and figures out which variables are only local or temporary, and then tries to infer some automatic uncomputation. And yeah, you see that here. So it uncomputes the comparison, and it also uncomputes the arithmetic. Okay, so Grover's algorithm also rather simple, I would say. Basically, you call the oracle and the diffuser in an alternating fashion, and then you get this circuit and this plot. We can see, so solutions are 0.5 and minus 0.5, which is indeed the solution of the equations that we initially considered. Okay, so that was it with the recap. So let me get to what we have been up to lately. Okay, so what we noticed, especially when writing the Shor's algorithm, is that we have a big scaling problem. And we see it here in this little snippet here. This is a modular in-place multiplication, which is the relevant operation for Shor's algorithm. And even for 35-bit, it already takes like 20 seconds to compile. So if we would ever hope to push it to 2000 bits, then this is not the way to go. And yeah, as you might imagine, because it is a Python embedded library, this is basically the origin of the problem. Python is very convenient, but it's also very slow. And yeah, this we started to tackle, and yeah, then naturally there were some considerations how people have been doing it in classical computing, because of course same problem also arises there. And there are basically three ways how people approach this, and I'm going to go through them now. So the first one is called C-bindings, second one is AST analysis, and a third one is interpreter tracing. Okay, so what are C-bindings? C-bindings basically means that you write the performance critical code in C and then use some special Python library like PyBind and expose it into your Python library. So here you see like a little folder structure, how this could look like. So you basically implement the performance critical part in a C file, and then you also have this Python wrapper such that your functions can be called from Python. So how does this relate to quantum? So one thing that is really neat about the C bindings, that you basically open your code base to the C ecosystem, which is of course probably the most popular high performance computing ecosystem on the planet. But debugging and maintaining C bindings is also much more cumbersome than Python code. And for this reason, C bindings really work best if you already know that the C function is not going to receive a lot of updates and it's going to stay state of the art for a prolonged amount of time. One example here is NumPy. In NumPy, we have matrix multiplication. This is an algorithm or a problem that exists for probably forever, but computationally it for a good 70 or 80 years. So there is not that much more improvement to be expected in matrix multiplication than we have already. So you just write the multiplication code in C, bind it to Python, and then hopefully forget about it. But this is not the case for quantum. In quantum, we have new methods for all kinds of problems constantly popping up. And if you want to develop a library based on C bindings, you're going to be much slower and more expensive with your team because you require highly specialized software engineers which are good at quantum algorithms and also good at C programming. So that is not the way that we wanted to go because our mission is to make quantum computing or performant quantum computing accessible. Okay, so second approach is something called AST analysis, and this basically means that you analyze the abstract syntax tree of the Python source code. And once you did that, then you kind of replace some predefined parts of it by some code of yours. And this way you can construct a quantum compiler that performs the operation that you want. And yeah, many libraries have been employing these strategies. From the classical side, we have Number, which is high performance Python accelerator. In quantum realm, we have CUDA-Q, Guppy, or Classic, which all employ the AST analysis strategy. But yeah, so the advantage of AST analysis is that you can have super clean source syntax. So I kind of like try to highlight it with this little snippet here, which is supposed to be a surface code encoder. So you have really clean control syntax. You can have the Python native loop statements, if conditionals, stuff like that. It looks really clean. But the big problem is that it can only execute stuff that has been explicitly coded by the developers of the programming library. And so that basically implies that you're not going to have access to the Python ecosystem. So that is also a big problem. And this is why we also ruled this approach out. Okay, so third approach, which is the one that we took, is called interpreter tracing, and is the unique mechanism that the JAX framework uses. And the idea here is basically that you take some kind of symbolic value and just send it through the Python code. Python has this duck typing, so it doesn't really care what is actually being sent through the code. So this works perfectly fine. And then these tracers kind of record what happens to them. And they record it into an intermediate representation that's called Jasper. And these Jaspers can then be processed by the XLA compiler. XLA stands for Accelerated Linear Algebra, which is yeah, something that is very fast. And yeah, the JAX is also very popular in machine learning. I think Google trains most of their machine learning and AI stuff with it, so it is definitely a heavyweight. Okay, so maybe let me give some code examples on how this works in practice. So this is just classical code for you to understand how it works. So you basically code a function. If you want to do some numerics, then you can kind of import this NumPy clone specified by JAX, which is called JAX NumPy, and then you just basically code the code as you are used to, and then call this function called make Jasper, and then you get this Jasper object out, and kind of looks like this. And yeah, you see here that it recorded what happened to the tracers, and this kind of representation is then ready to be pushed through a compilation pipeline. Okay, so how does this connect to quantum? There's this really cool framework called Catalyst, and Catalyst also kind of realized that scaling is going to be a problem, and what they did is they wrote their system of expressing quantum computation, or to be more specific, penny lane scripts into JAX expressions and lowered them into MLIR/QIR, which basically opens all of this to classical compilation infrastructure, and therefore a lot of scaling advantages. And yeah, so Jasp is basically the combination of all of this. So with Jasp we have the amazing Catalyst scaling features with the CRISP programming model. And so this basically gives us this stack. So on the top we have CRISP, which traces itself into an intermediate representation called Jasper, which is similar to Jaxper, but it's Jaxper with quantum. And then we convert it to the JAX dialect of Catalyst, and then this is like subsequently lowered until it is run on a hybrid backend. But besides just QIR compilation, this approach showed to offer many more features that I will also talk about in a few minutes. Okay, so how does this Jasper IR look like? Similar to the JAX script, I made a version with quantum, and here you can see the CRISP code. Basically, it just defines a quantum float, applies some gate, and then measures it. And instead of make Jaxper, we now have make Jasper, and then we get this. So I would say it's a rather simple and restricted IR for expressing quantum computations. The amount of primitives is limited. You can create qubits, you can retrieve qubits from qubit arrays, you can apply some quantum gates, more quantum gates, and here measurement. And one important detail here is that the measurement simply returns a normal integer. So it is very smoothly integrated into the JAX ecosystem, because with this integer you can now do whatever you want, all kinds of JAX gymnastics if you want. So, and then yeah, so this is a reset, and this is freeing up the qubits. This is the memory management that I talked about. So basically some kind of garbage collection which happens automatically here. If you want, you can also turn that off. Okay, so now we have our Jasper object, and now what can we do with it? So first of all, you kind of want to make sure that your script is correct, so you want to run it on a simulator, and for that you can simply call it like a function, and then it will connect to the CRISP simulator and evaluate the script. So second important feature that I already talked about, you can call this methods .toQIR or .toMLIR, which compiles the strings for that. And if you happen to have a backend which can run these representations, then you can run it on your quantum computer. So furthermore, there are also some more compilation relevant methods. So you can call .control, which generates the control Jasper. You can call the inverse. It's also possible for you to specify a custom control version for your function. So many papers, additionally to their implementation for an adder, for instance, they also say how you can execute this adder in a controlled manner efficiently, instead of just naively controlling everything. So that's called that's what we call a custom control, and you can specify that. And it's also possible to specify a custom inverse. Now you might think, okay, so performing the inverse, there is not that much performance overhead. It's just staggering everything. Well, yeah, there are some quantum functions which can be implemented efficiently if they contain measurements, some feedback, and of course that cannot really be inverted that much, and for that reason you can also give a custom inverse. And then there's also this .toQC method and the toQASM method, which kind of attempts to extract the quantum circuit, but that's not really always possible, and why that is the case I will now get to. But yeah, before I'm gonna talk about one more crucial advantage of tracing compared to the AST, and that is that if you really want to do state-of-the-art compilation, you cannot just stop at looking at circuits and putting out a better circuit. Many optimization steps also happen on a higher level, and to realize these optimization steps, you need some good classical infrastructure. One example here is trotterization of a Heisenberg chain, which has this kind of Hamiltonian. And the key observation here is that these terms don't really commute. So if you just look at the quantum circuit, you have no way of saying, okay, yeah, I could exchange the order of these, but the trotterization algorithm doesn't really say in what kind of order you should execute it. So even if the trotterization terms don't commute, you're still allowed to exchange them because there is no preferred order to execute them. And yeah, if you just naively compile the Heisenberg chain and you have bad luck, then you might end up with this. But of course, this is much better. And so if we now want to scale that up, we in CRISP use some graph coloring algorithm, which basically tries to make sure that there are as few layers as possible. Basically, every layer corresponds to one color. So if you have a good graph coloring algorithm, you also have a few layers. And in AST approaches, you have no access to graph coloring algorithms because the only accessible infrastructure is the stuff that the SDK actually program themselves. While with the tracing approach, you have the whole Python ecosystem at your hand. So that is, of course, an important and critical advantage to have this compile time infrastructure available. Okay, so now some words about what it is like to program in Jasp and how it is different from normal CRISP. So writing the programs in Jasp is rather similar to writing the programs in JAX, and a key distinction that you have to understand here is the difference between static and dynamic values. Dynamic values, or let's start as static. Static values are just your everyday Python variables that are known to the Python interpreter once the interpreter executes the script. Dynamic values are values that are only known at execution time. So for instance, if a measurement is coming out of your quantum computer, you of course don't know what the result of the measurement is going to be, so you don't know it at compile time. And this is reflected in the notion of dynamic values, that you don't know it at this point. But it doesn't necessarily have to be a measurement. It can also be other types of values. In general, quantum variables, you can basically always treat them as dynamic, especially their size. So the size is the amount of qubits that they contain. Measurements are also always dynamic, or the results. Can just allocate a regular Python integer, then of course that is not dynamic. Can also just use whatever Python library you want to use, for instance, network X here, and then that's also static. Okay, and now another really important advantage of Jasp over normal CRISP, that is capable of representing real-time computations. So real-time computations means that you measure something in your quantum computer, and while the quantum computer stays coherent, you do some classical task, and once this task has concluded, the result of this computation is fed back into the quantum algorithm by, for instance, some conditional execution of a gate. And these real-time computations in Jasp are represented through the JAX NumPy, which is basically the traceable clone of JAX. So you can really express a lot of classical processing steps, basically everything that you can also do with NumPy. And yeah, as I already said, the measurements in Jasp just return regular JAX data types. So you can just treat them as classical values and at some point feed them back. Okay, so let me also say a few words about this code here. So here we allocate a quantum array, which is basically an array of quantum variables. And if we measure it, we receive a classical array. We can increment it. We can use the scalar product, j and p dot dot. And can also have this classical quantum addition here. So in the quantum array, there's the quantum variable, and we increment it by this scalar product here, which is really the result of a real-time computation. And yeah, finally, we measure and return. Okay, so how can we do the control flow? Also rather similar to how it is done in normal CRISP. In normal CRISP, we have this thing called control environment, and we kind of extended the meaning here to also classical controls. So in this control environment, you now can also feed classical booleans, and then the indented area here is going to be executed conditionally. So what this script does is brings a quantum float into superposition, measures, and then if the measurement is less than 4, it increments the quantum float by 4. Okay. And yeah, so now about the performance that I was mentioning earlier. Why is this more performant? So there are two important things here to consider, and the first one is dynamic loop capturing, and the second one is call graph compression. So what does dynamic loop capturing mean? So in normal Python, if we would have something like that, maybe without the J, it would just execute this loop 10 or 10,000 times, whatever. But within JAX, or within Jasp in particular, what this does, it only executes this loop body constant amount of time to actually, and then kind of stores the fact that this is a loop. So it doesn't like store a bunch of CX gates, but it stores the fact that this is a loop. And of course, this can dramatically reduce the tracing effort, in particular if you're operating like Shor's algorithm on quantum variables with thousands of qubits. So can really dramatically reduce the tracing effort. And another important aspect here is that it also reduces the transformation effort. So let's say we have an adder here, and I want to have the controlled version of this adder. In a non-static, in a non-dynamic quantum programming language, you would have to generate the controlled adder 1,000 times if this loop contains 1,000 iterations. But here, because the whole thing is captured in this rolled form, you only have to generate the controlled adder once and then simply go with that, because the loop is kind of captured symbolically. Okay, so second mechanism is the call graph compression. So the idea here is that if you have a subroutine that you know can be kind of encapsulated, then it is possible for Jasp to tell it by using this cache decorator here, and then it will capture the representation of this and then simply continue to refer to this representation instead of capturing it again and again and again. So we can see that here. So we have this function init ghz, and we use the cache decorator, and now we have the cached version. And if we call it now 3 times, this function here is only going to be executed once, and for the other 2 calls, it's gonna be the intermediate representation, the IR, which has been traced before, that's going to be referenced to. And also here, we have constant tracing effort regardless of how many times we call this. And we also have constant transformation effort. Because again, if we would need the controlled version of this, then we can simply also cache the controlled version. And if we would need the control version of this, then we simply retrieve from the cache. So that is also a really powerful tracing effort reduction mechanism. And we can also take a look at how this looks in the IR. So we see here this Jasper IR, which I already introduced. And we see 3 calls of this pgit primitive, and it refers to this Jasper init GHZ, which is defined once and not 3 times. And that is the key point here. And yeah, this is what I call compressed. And it should also be mentioned that this compressed feature is preserved through all the transformation steps. The call graph stays compressed such that even at the MLIR, the whole thing is compressed. Okay, so now some cool things that we did with Jasp. Okay, so maybe just for starters, the measurement-based uncomputation, maybe not as spectacular, but maybe to understand. So yeah, first of all, what is the measurement-based uncomputation? It's basically a way to save some C0 and T gates for computing intermediate AND values. So computing intermediate AND values is something that happens a lot with a lot of algorithms. So saving gates here is something that is very desirable. And for that, Craig Gidney in his paper, Halving the Cost of Quantum Addition, came up with this measurement-based uncomputation circuit here. And so basically you compute like this and you uncompute like this. And as you can see, the uncomputation takes 0 T gates and only 0.5 Clifford gates, 0.5 because this measurement will return 1 in only half of the cases. And yeah, you can also see the code here, which which is rather self-explanatory. Okay, so now I should accelerate it a bit. Yeah, so iterative quantum phase estimation is rather similar to quantum phase estimation, but the key difference here is that you kind of classicalize it in the sense that you perform classically controlled rotations instead of quantum controlled rotations. And yeah, it's reflected in this circuit here. And yeah, so probably not going to have too much time to go through this. But yeah, maybe if you want to look at the slides later, then you might recognize that this is indeed the code that performs iterative quantum phase estimation. Okay, so now hybrid algorithm compilation from the NISQ regime. So what we today see a lot is that we have hybrid algorithms in the form that the Python interpreter computes something, maybe some optimization algorithm, send it to the quantum computer, and then the feedback loop goes on. What we do here is we kind of not go to the Python interpreter all the time, but we simply send compiled binary, do the optimization, and simply return the results. And how does this work? It works basically with the same code as with normal CRISP. So we implemented this traceable optimizer, SPSA and Kubila. And yeah, this is the code that sets up the VQE for the H2 molecule with the QCCSD ansatz, and it compiles a QIR string that does the whole workflow within just a few lines of code. Okay, so HHL is an algorithm that has an exponential advantage for where it is applicable, but we couldn't really find any implementations that would compile the whole workflow. Why? Because this repeat until success thing is also, again, some kind of real-time feedback, and it also has a very strong requirements regarding the algorithmic primitives, Hamiltonian simulation, quantum arithmetic, and quantum phase estimation, and it's also difficult to coordinate all the moving parts if your system of abstractions is a bit cumbersome. Okay, LCU, another algorithm which requires real-time feedback that we couldn't really find where it's like implemented in its full wealth. And yeah, that's also available. All of these are documented on the CRISP website if you want to look into it. Okay, so now the reason why I went a bit faster, because I think this is a really interesting topic. So what is a reinterpretation? Within Jasp, we build some infrastructure that allows us to kind of reshape and manipulate this Jasper IR. And what does that mean? It's basically possible for us with this interpreter infrastructure to implement custom behavior for each of these primitives that we have. So here's a little very simple classical example. On the left-hand side, we have a Jasper which contains 2 multiplications and 1 subtraction. And now we kind of transform it by assigning a new behavior. And the new behavior is that each multiplication should, before it multiplies, increment the second operand by 1, and it multiplies with a negative. And yeah, you kind of see that here. So this is just to show you that this kind of thing works, and we have the infrastructure for that. And now we can start transforming the quantum computations that are expressed through Jasper. And actually, many of the features that I already introduced are based on this interpretation mechanism, for instance, binding to the CRISP simulator. So basically the way that all the gates are receive their behavior is by binding it to the CRISP simulator. Also, converting to Catalyst for QIR generation is an interpreter. Applying invert and control transformations, and in general all quantum environments and higher order functions are also realized via this interpreter features. Okay, and now some other interesting interpreters. Static quantum circuit emission, that's pretty cool, but the real gems here are a Boolean simulation and resource estimation. Okay, so what does Boolean simulation mean? So basically, what we see is that there are a lot of quantum algorithms that take these classical oracles. So for instance, Schroth's algorithm, quantum walks, some Hamiltonian simulations that compute the entries of the Hamiltonian. So these are purely classical functions. But if you want to verify the correctness of this, even the strongest simulator can fail for even toy problems. So there is an actual use case for simulating quantum code that is purely classical. And for that we have the Boolean simulation reinterpretation. And the idea here is basically that if you have a Jasper with only Boolean logic, that is X gates, CX gates, CCX gates, and so on, then kind of reinterpret this by viewing the circuit simply as another integer, and then we perform the equivalent Boolean operations. So yeah, we have the shift left here, which indicates that we want to address the 8th qubit, and then we do the XOR gate to reflect the X gate. Okay, so resource estimation is also an extremely important problem, because it's currently not really that known for what quantum computers are actually going to be good at. So we need to kind of gauge which algorithms could potentially deliver us some advantage. And for that, we need to go to practically relevant scales and measure how many gates are required. But here comes the problem. There are tools for that, but they usually only allow you to do some kind of approximate implementation, so it's not really possible to figure out if your implementation is correct. It just is just like hand-wavy a bit. And what the resource estimation interpreter now allows us to do, to simply transform the exact same code into a program that compiles a binary which computes the resources that are required. So here we have again a Jasper which executes a T-gate, an S-gate, and a T-gate. And now we represent the quantum circuits as the corresponding counts of the gates. So this is probably going to be the count of the T-gate. This is going to be the count of the S-gate. And now we simply increment these counts every time, and yeah, we return the counts. And yeah, there is some benchmark here where we simulate the beryllium hydride molecule with our trotterization and quantum phase estimation functions. And yeah, we count the resources. Here you see this count ops decorator. So most of these reinterpretation things, they're accessible through some kind of decorator. So you just write the script, and then you put whatever decorator you feel like. And yeah, so the resource estimation is really fast. So compared to Qiskit, it is 1 billion times faster, and it is also, like, the implementation is also more efficient, almost 1 order of magnitude better in CX count. Okay, so summary. With Jasp, we could connect CRISP to classical compilation infrastructure via the Catalyst framework. We made it possible that it is fully agnostic to scale, and yeah, we also could implement several other interesting execution modes. In contrast to AST-based compilers, we can leverage the Python ecosystem, and with Jasp we remedy some important weak spots of CRISP, and that is long tracing time, lack of real-time computation, expressibility, and difficult code analysis. Okay, thank you.
Yes, thank you very much, Raphael, for this outstanding talk. Now let's come to some questions. Oh yeah, there's number 1.
Very, very cool stuff, Raphael. I'm really impressed. However, I must defend the honor of the AST approach against your cruel attacks. So the point is, in the AST version, as used in Guppy, you can do everything in the Python environment at compile time, which is kind of the same as what you're doing in CRISP as well, right? The difference between dynamic and static. In fact, you even have a stronger thing, which is that it's syntactically distinguished from stuff that happens at real time. So you have fewer programmer errors this way. And the point about whether you need to maintain this knowledge of the source level program at compiling is kind of also assuming that you've thrown away everything and it's like one big lowering of compiling. But you can do it in a more structured way where you can retain the structure and work with it as you go down, which is what the ML and MLIR stands for, right? So I think the AST approach is very good, and then you don't have to do some of the workarounds that you have in here, like the call graph compression, which we just call generating code for subroutines and similar things. So yeah, I just want to say that it's not as bad as you made it sound.
Yes, I mean, I'm aware that this is possible in Guppy, and sorry for not mentioning it, but it should also be mentioned that the interface for doing that basically allows the transmission of very, very simple data types. So it's like tuples, lists, and that is basically it. So that is, I would say, also it is not optimal. So having it simply like a normal, like you would normally program it in normal Python, it for sure allows better integration of these things.
Yeah, I think you should also think what will actually run on the real-time system. Like NumPy is not going to be there, right? We're not.
Yes, but NumPy also runs on the. No, you're talking about NumPy. I thought you're talking about Number. But yeah, I mean, it depends what kind of algorithm you want to implement. So maybe there's some kind of feature where this is required.
I have one completely orthogonal comment as well. The stuff what you called a reinterpreter, I would like it if you called it something else, because it's not an interpreter in the usual sense, right? It's more like a rewrite system or a transformation system. Very cool things.
I can also call it differently if you prefer that, but yeah, I mean, I guess I could bring the point.
Yes, thanks for this nice talk. So I was wondering, when you do the control or the inverse, is it which level it is at? So do you need to know the number of qubits of this unitary or procedure, or to obtain the control version of it?
Yeah. So right. So the way that this control method works, it basically inserts MCX gate at the beginning, at the end, computes some intermediate control value, and then all the quantum instructions, they receive one additional control. If there is a one of these cached functions, so like this this call graph compression thing, and it contains a custom control, then this custom control is used. Otherwise, the whole procedure is called recursively.
Okay, so when you add one additional control qubits, then ultimately you would need to further decompose it into 1 and 2 qubit gates at the lowest level, right?
Yes.
And this is independent of this part, right?
Yes. So this kind of task is part of the non-dynamic CRISP. So the non-dynamic CRISP already has all the algorithms implemented that are required for this basic tasks of generating controlled operations, stuff like that. So for that, we just use the normal CRISP infrastructure.
Okay, thank you. Maybe another question. So it's about Grover search. So when you, I assume you can embed, you already embed the oracle synthesis in when you specify the oracle by writing some function, classical functions to for the marked item, right? Because you can specify the marked item using some functions, right? So you already implement the oracle synthesis in this part.
Yeah, the oracle synthesis, I mean, what is pre-implemented is the arithmetic and the comparison. The synthesis of the oracle itself is done by the programmer. Like the programmer writes the code and plugs together the functions, and then you have the oracle.
So it is not automatic synthesis of the oracle. I mean, is it the duty of the programmer to write how to specify this oracle, or it is a compiler or the automatic part that performs?
There are also there is also a feature in CRISP that's called quantum dictionary that would do this automatically. But in general, this doesn't scale because the quantum dictionary doesn't know anything about this arithmetic structure that is in this oracle. So it just like general logic synthesis routine, and we could also do it like this, but it doesn't scale. So there's also an automatic solution to this.
Yeah, I see. Okay, maybe one more question is it possible to implement nested Grover, for example, for the outside Grover, the marked item is specified by an inner Grover, the result of the inner Grover. Is it possible to do that?
Yes, yeah, that works. I already tried that out, yes.
Okay, thank you very much. Very cool.
Thanks.
Hi, thank you so much for the talk. So I think you mentioned about the hybrid algorithm, classical, especially for the quantum machine learning, I think. And currently you have mentioned that optimally we should only update the parameter for the algorithm, not compiling all of the circuit within the quantum loop or the classical loop to update the parameters. Recently I've seen that there is a paper publishing how a circuit we can stream the data directly into during the runtime, real-time in quantum computer. What do you think of this use case if we can stream data directly like that?
So the reason why people used these parameterized circuits is because exactly of these recompilation issues. You don't want to go through all the compilation again and have to do all the steps and then only to receive the circuit with updated parameters. But in this case, we don't have to go through the circuit, through the compilation routine anyway, because it is already in a low-level representation. So the execution engine kind of already generates the updated parameters. So this kind of problem that we would potentially lose performance by going through compilation again doesn't appear because it is already compiled.
Okay, thank you.
Yes, so I think there's probably more questions, but we'll take that offline then. Then thank Raphael once again.
Thanks.